Hello and welcome to a new video series. In the past, I have done Advent of Code in a more competitive fashion, but this time around I decided what I wanted to do was to instead solve the puzzle ahead of time, then do a video talking about how you might TDD yourself into the solutions to the problems that we have. So we're going to start today. Today's day one, so let's go ahead and get started. Okay. Here's our problem text. You haven't even left yet. The group of elvish senior historians has already hit a problem. Their list of locations to check is currently empty. We're looking for someone. Eventually, someone decides that the best place to check first would be the chief historian's office. Upon pouring into the office, everyone confirms chief historian is indeed nowhere to be found. Indeed, the elves discover an assortment of notes on a list of historically significant locations. They seem to be the planning list for chief historian was doing before he left. Perhaps these notes can be used to determine which location to search. Throughout the chief's office, the historically significant locations are listed not by name, but by a unique number called a location ID. To make sure they don't miss anything, historians are split into two groups. There's one problem. By holding the two lists up side by side, your puzzle input, it quickly becomes clear that the lists aren't very similar. Maybe you can help the historians reconcile their lists. There's our first sample data. Right there. Maybe the lists are only off by a small amount. To find out, pair up the numbers and measure how far apart they are. Pair up the smallest number in the left list and the smallest number in the right list, then the second smallest and the second smallest, and so on. Within each pair, figure out how far apart they are. So you start out with if you have a 3 and a 7, the distance is 4. If you have a 9 and a 3, the distance is 6. The reason that this is worded the way it is 3 is less than 7. So 7 minus 3 is 4. 9 is greater than 3, so if you did 3 minus 9, you'd get minus 6. So they're just warning you that the bigger number might be on the other side. So, in the example list above, 1 to 3 is 2, 2 to 3 is 1, 3 to 3 is 0, 3 to 4 is 1, 3 to 5 is 2, 4 to 9 is 5. Add all those up, you get 11. So, they actually also have a larger set of data, and this is the answer I came up with, a larger set of data. So I've already obviously solved the problem once. So let's go take a look at the data files that I've created, right? So that's our original sample data. You can see we have 6 lines of unsorted data. And then over here, you can see in the real data, we have 1,000 lines of unsorted data. So we know roughly what the data looks like. We can see the data in the real data they're 5 digits long, so easily fits inside of an integer. There's 1,000 items, so easily stores in memory, no problem. 1,000 integers, not a big deal. So if we were to TDD our way into this, what would that look like? Well, for starters, let's say we don't know what these tests are of yet, so we'll just call them tests. Let's do this. We're going to do a theory, which means a data-driven test in xUnit.net. And we're going to say, given the data in data1.txt, we should get 11. And given the data in data2.txt, we should get, what is it? It is this number here. Okay, so we should get that number there. Call this part 1, and the data will be expected distance. Oops, expected distance. Okay, so we know we need to do some things, right? We need to read the lines out of the file. We know we need to sort the lists. We need to compare for distance. And then ensure we got the right answers. Okay. What if this looks like test code and what if this looks like production code? Well, I think this kind of looks like production code. And that is our test code, right? So we could say assert equal expected distance, actual distance. We don't have an actual distance yet. Go ahead and put actual distance in here as 0 just to start. And then to run these tests, right click and do run tests. If you do that, that'll run them in Test Explorer, but also with XGene.NET version 3, you can just run this. Your test project is an executable, so if you just run this, it will run your tests. And we can see here, we expected 1 and got 0. We expected 3 million something and got 0. And you can see it's telling us which set of data resulted in that failure. Okay, so this is good. All right, we have our test. Our test is now failing. Let me do a clean so that this green check mark will go away. I think the green check mark will go away eventually. Go away. I don't know. All right, so yeah. So we now, there it goes. So now we have our failing test. All good. We need to, that was this. But we need to do this. So from a production perspective, what does that look like? We're going to call this our distance computer, right? So I guess one thing we could say is public int compute distance given a file name, right? So we'll go ahead and for now, we'll go ahead and return 0, and then we will compute the distance. Compute the distance. Distance computer, compute distance. Yeah, it's not static. I'll go fix that. Given this file name. Okay. So then this stuff comes up here. All right. And yes, you're static. Okay. So now we run our tests again, and we'll still see that we fail with zeros because, of course, we were putting zeros in there. So we need to read the lines out of the file. That makes sense. So for each var line in file, read lines, read all lines out of the file name. That's the operating system or the .NET Framework version of saying, hey, get me all the data in this file one line at a time. So for every line that's in there, we need to parse it into its two pieces. Right, so we'll line split on spaces, and we notice that in the data that we've got multiple spaces. So the other thing we want you to do is we want you to do string split options, remove empty entries. So what that will do is when it sees this line, it will split this into two pieces. If we didn't have the empty entries, then we'd have 3 and an empty space and a 4, something like that. So we just want to get rid of all the empty entries. Okay. We know we need, we'll do a list event for the left. All right. And we'll do a list event for the right. Okay. And then we're going to say left is int parse pieces sub 0, pieces sub 1. Okay. Oops. Sorry. Pieces sub 1 is, we're going to add this. What happens when you don't plan ahead? Add this to right int parse pieces of 1. Okay. That's going to get us left and right. So we have read the lines out of the file. Okay. So that's so far so good. We need to sort the lists. List of T in .NET very conveniently has sort already. We're going to sort the lists, and then we got to compare for distance. And the idea is the lists are equal size left and right. So we take first item out of each list, compare, next one, compare, next one, compare. We're going to add them and keep them all together, right? So we're going to say the result is 0. We're going to return the result. Then we're going to say index is 0, index is less than left count. Total plus index, we're going to say result plus equals the absolute, because remember, we don't know which one's bigger. We don't really care. Left of index minus right of index. Okay, and then we're going to return the result. Let's see how that looks. Okay, now we have 2 passing tests. So clearly that is the right algorithm that they wanted. Looking at this, are we happy with all of this? I mean, I see, we have the reading of the list, we have the sorting of the list, then we have the computing of the list. That's 3 things. Maybe there's 3 things that come out of this. For the moment, I think I'm okay with this. We'll see what the second half of the problem looks like. Okay, so second half, part 2. Your analysis only confirmed what everybody feared. The 2 lists of location IDs are indeed very different. Or are they? Historians can't agree on which group made the mistakes or how to read most of the chief's handwriting. But in the commotion, notice an interesting detail. A lot of location IDs appear in both lists. Maybe the other numbers aren't location IDs at all, but rather misinterpreted handwriting. This time you'll need to figure out exactly how often each number from the left list appears in the right list. Okay. Calculate the total similarity score by adding up each number in the left list after multiplying it by the number of times that number appears in the right-hand list. All right, so here's the example data again. First is 3. We see 3 is over here once, twice, 3 times. 3 times 3 is 9. When we go look for 4, we see that 4 is over here only once. 4 times 1 is 4. We're adding all these numbers together, blah, 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 blah. So we should get 31. And then given our big data, this is the answer that we also got. So let's go grab 31, and we'll do part 2. Avoid part 2. And int expected similarity is what they called it now. All right, we're going to say actual similarity. Right now, we'll just say 0. Assert equal expected similarity, actual similarity. And this is yelling at us because we haven't started doing data yet. We need to mark it as a theory. And we're going to say data1.txt. Our similarity was 31. And then data2.txt, our similarity was this big number over here. Okay, now if we run the tests, well, they should fail because obviously we have not written anything yet. So there we go. Those are now failing with zeros. We can obviously start here with now saying distance computer compute similarity, given this file name. Go ahead, generate that method up here. Make you public. Async enumerable of objects. For real? Okay, how about just int? Okay. We can leave the throw not implemented and then run our tests and we'll see. Throw not implemented, that sounds great. So now we have to compute the similarity. Let's not worry about this up here much, other than we're going to copy some stuff, right? Because reading the list is exactly the same. This is going to be a clue for us to come back later, but at the moment we're just trying to solve the problem. All right, and then we have a result is 0. Turn the results. So again, we'll run, and we should now see zeros again, where those are failures. Okay. And so what we need to do is we need to go down the left-hand side of the list and say, given what's on the left, find how many times it is on the right. And one of the tricks with these kinds of problems is thinking about the algorithmic optimization, right? So if you're a computer science student or were in the past, you might have heard of big O notation. So big O notation generally is talking about loops, okay? So if we're to look at this loop right here, right, and say for every line in the file, we do one thing, okay? That would be a big O notation of O of n. What that basically says is for each item, so in this case, for each line in the file, we're going to do one thing. So there are 10 lines in the file, we're going to do 10 things. So that's what O of n is 10, right? If we think about this computing the similarity, the brute force way for us to do this would be to basically say, let's do this. For each left item in the left, we'll do the brute force version first, right? So for every left item in the left, we're going to say similarity of this starts at 0, right? And then we're going to say for every item in the right, All right, we're going to say if the right item is the same as the left item, then we've got one piece of similarity, right? And then the result is plus equals the left item times the similarity, meaning how many times we found it. Similarity is a terrible word there, then we'll call that occurrence. So every time we saw it, we increment it by the occurrence. That is exactly what they asked us to do. Algorithmically, we can see we have a loop inside of a loop, right? So what that means is, in this case, we have O of n times O of n, which is O of n squared, right? We have 6 items in the loop, and like we do in the data, right? We're going to have to look at every item here once. And then for every one of these, we're going to have to look at every item here once. So that means 6 times this times 6, right? So that's 36, right? That's 6 squared. So that's O of n squared. In our 1,000 item list, right, that means we're going to have to look 1,000,000 times, right? So that could be slow. Is it going to be slow enough for us to worry about it right now? Probably not, but let's see what happens if we try and run it. In our case, no. Turns out that's perfectly fine in a language like C#. C# is easily able to do 1,000,000 computations in essentially, 76 milliseconds. And that, of course, includes the amount of time we spent working on part 1, which was linear. So, given that, we now know that we definitely have at least this code in similarity with this code, right? So we can now do in TDD what we call as a refactoring. And refactoring basically just means you're going to change the production code without changing the tests, without making the test. You start with your tests in a passing situation, you change the production code, you rerun the tests, make sure the tests still pass. All right, so in this case, we can extract out this code and say, you are read values from file. Okay. I don't like exactly the way that it told us to do this. I don't like passing in and viewing out and whatever else. So we're going to take this over here. All right. We're going to say, hey, you and you. And then we're going to return in C# what's called an unnamed tuple, or an anonymous tuple, I guess, since we're going to actually use names. We're going to return a list of int called left and a list of int called right. Okay. And then the result of this is going to be return left and right. So then up here we have file contents. So what exactly is this? Returns left and right. This file contents left is an int, is a list of int, and file contents right is a list of int. Well, you can helpfully also see that this thing can be deconstructed. So what that means is it can turn this anonymous tuple back into individual values without having to hold the whole tuple itself. So let's see what happens when we do that. Deconstruct. There we go. We've got var left and right is read the values from the file. And so right now, just with this as it is, which you're private. Okay, good. So now if I run the tests, part 1 still passes. Now I have this similarity that I can take out here, and I can say var left and right is read, what did I say? All this. Read values from file. Given this file name, we can read this. Okay, that's good. So there we are. And everything is still passing. We're still at 76 milliseconds. We haven't really introduced any craziness here. So one thing you'll notice that we've done in common here is that we've done twice is we've had to actually read these values from file twice. So this right now is all statics. So the next thing we could do from a design perspective is we could turn this into a class and not have these be static, compute distance or compute similarity. Right? We could turn this into a class, and the class could store the left and the right data. What's interesting about this from a design perspective is, it prevents us from having to read the file twice. Really, what we're trying to do, prevent reading all these files twice. So if we were going to do that, what we'd want is something that could basically create an instance of a distance computer, starting with a file name. Like maybe we make the constructor take a file name, and then it will read the values from the file in the file name, right? So given that, let's do this, right? So what might you look like? Let's say public distance computer, right? If I were to actually move this code up there, and I could still call the static, but we're headed in the direction of an interesting design, I think. And if I had that, then I had non-static versions of these, right? Then I could compute it all that way. But I don't want to change tests and production code at the same time. So I have two ways I can do this, right? So we'll call this the static tests, and then we'll call these the non-static tests. Non-static tests. So we're actually going to evolve the design of this class, this computer class, by basically causing it to show up as a TDD item. So what we really want then is we want to be able to have these things be able to be used in this way so that we could reuse the data if that's what we decided we wanted to do, right? So what we're going to do for that then is let's think about what these tests would look like. We had the data sitting here, for example. Public, not public, static, read only the computer, right? This would be data one, right? So if we made a new distance computer for data1.txt, and then we made a new distance computer for data2.txt, right? We're just kind of spitballing here on what this might look like. Let's write part one again. So given this, right, so given part one, what we'd actually want to do here is instead of our inline data being data1.txt as a file name, what we really want is this to be data1. But of course, you'll find that we can't actually do that. All right, we want distance computer. And then we want this to be compute distance. Now we don't need the file name anymore. Okay, this is a function that doesn't exist yet, just like this constructor doesn't exist yet. So we've got some complaints here. Data one, okay, an attribute argument must be a constant expression, type of expression, or array creation expression of an attribute. Okay, so it's basically saying is this isn't a constant. You can't use it like this. So what can we do? Well, we can say this. We can say public static enumerable of theory data row of distance computer and int. That'd be part one data, right? And then what we're going to return back is come on. And this big number. Right, so that's what we want. And instead of inline data, we're going to do member data. Name of part one data. So the complaint here is that that number was too big. So there we go. All right, so given this, argument data might not be serializable. Not worried about that. So given this, now what we're missing here is we're missing our non-static compute distance and our constructor, right? So first thing we need then is the constructor. Right, and we know we need to do the read values from lines. And from a value perspective, we know you need to keep the left, right. Okay. So given the left and the right, we're going to say left and right is this. Okay. Now, compute distance, a non-static version of compute distance, looks pretty much exactly like this, except it's just this. All right, it's just that. Okay. And then this static version we're going to leave here because the old test still requires it. Now, if I come back down here, we have all of this. You're just telling me I can make that be less text. Thank you, I appreciate that. Okay, now if I run these tests, and now see we have all 6 tests passing. Okay. Now, from my perspective, since we're evolving, we've just replaced one test with another. This test can go away, right? And we can go back to just having 4 tests passing, which also means now that this static version of compute distance has nobody asking for it anymore, which means you can now go away. Now, still have 4 tests passing. Okay, so let's do the same thing for similarity. Okay, so public static, I enumerable, theory, data, row, distance, computer, int, part 2 data. Part 2 data going to look like this. We're going to say new data 1, 30, was it 39? I forgot what the number is, 31. Okay, and then we'll do new data 2 with a big number, right? And then we're going to write this theory, member data, name of part 2 data. Part 2, just like part 1, takes the distance computer, expected similarity, right? Computer in, does computer in, what's your problem? Name of part 2 data. Yeah, that's not a name. That makes sense, right? And then we're going to, the test is going to look exactly the same as this up here, right? Except we don't pass the file name anymore. And we use the actual computer instance to compute the similarity. This function does not exist yet. So we'll go ahead and we will generate that method. We will run these tests, watch it throw the not implemented because we just generated that method. It's not implemented, right? So this compute similarity, I love how it always is. Obviously you meant this to be internal, is exactly the same as this compute similarity, except yet again, we already have the left and the right from the constructor, so we don't need it anymore. Okay, so now we can run this. We have 6 passing tests. That's good. That means that this test is no longer necessary. We'll get rid of that whole test class. Go back to just calling you tests. We'll run this. We have 4 tests. We have a static function that, there we go, as soon as it gets updated, we have no more callers anymore, so we don't need this function anymore, right? So now we have compute distance, compute similarity, read values from file. What's interesting is we only have 1 reference now. So remember we had that commonality that we extracted out into this function. We don't necessarily need that, right? So we can just take this out now, right? We'll refactor that up into here. And we will start by saying left and right are empty. We don't have to return anything. Those things just get read from up here. Now we run our tests again. There we are. 4 passing tests, same amount of time. So from a design perspective, are we happy with this? I mean, it seems reasonable. There is this, like this actually sorts the data in place rather than giving you a sorted version to work with. Not necessarily happy with that because it manipulates the data that we read and it's no longer the original data. So from a data purity perspective, if you really wanted to not do this and instead do something else, what you would do is you would say sorted left is left order by the value. Sorted right is right order by the value. Right, and then these need to, we'll make, oh, whoops. Turn those into arrays. Doesn't matter, we're just going to turn them into something. We just need something. Because now we're going to use sorted left. I guess since we used count, we should turn them into lists, right? So you'll be a list again. So the sorted left and the sorted right. Okay. This feels a little bit better to me because now we have the original values are still standing here. And in fact, it's telling me I should make these read-only, so that's exactly what I'm going to do. I'll go ahead and make those read-only. But read-only doesn't mean what you think it means there, interestingly. Okay, so our tests are all passing. They're still taking the same amount of time. So I think in the end now, I'm pretty happy with where distance computer is, right? This is our initialization work, which is start up by reading all the data. Our compute distance now does not destroy the original data in favor of a new sorted version. Our compute similarity works with the data as it is because it didn't really need to manipulate it at all. And our tests are still in a good place, right? 31 and 2.6 million or whatever. Yeah, 2 or 26 million, okay? Also, for those of you who don't know, C# added this quite a long time ago. If you want to put these in here, help you see the numbers. And actually you can put them wherever you want, which is okay. I don't know, maybe that's help you see that better. Anyway, so I think we're pretty happy with where this code turned out, right? And we sort of let it evolve. We used TDD to sort of make it happen. We used sort of the red-green refactor classic of TDD, which is make the test fail, go implement some code until the test passes. Keep doing that in a loop until you feel like, you know what, the production code is getting a little bit messy, and so I want to change it. So for us, that was part 2. And I think in these TDD examples, you're going to find that that's pretty much exactly how it's always going to work. We're going to get to part 2, and we're going to say, well, where's the commonality? We didn't know what the commonality was. We had to wait until part 2 to find it. That's actually not all that uncommon. So you'll find that as you are sort of designing these things, maybe the design you thought you had in your head to begin with is good. Maybe it doesn't turn out that way. Sometimes you just implement the code in the tests. Don't even make separate classes until you feel like, okay, well, I now understand exactly what it is I'm asking this thing to do. You know, in these cases, it's a little bit hard with TDD to say, this is how exactly it should be done, because there's, you know, step 1, step 2, step 3. You really only have 2 steps. So we really only generally have 2 tests here. Although we could go back and we could now implement tests against the test computer itself. Like we could say, after you read the data, was the data read correctly? Which would mean we would expose the data to being read in the test. Because right now, the data isn't readable from the test. It's only readable from inside the code. So those are decisions that you can make. But I think as a day 1 example, right, this should be pretty good. Should get you on your way. So hopefully that was helpful to see the sort of TDD thought process. Those are very simple problems. So I expect as the problems get more difficult and more challenging, that the examples will probably be a little bit more involved. So hopefully that's the case, and I will see you next time.